Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 10, Video 5. Today's topic is angular momentum. The objectives are: know the definition of angular momentum of a particle, know the definition of angular momentum of a rigid body, understand the rate of change of angular momentum of a particle equals the total torque, the net torque acting on it, and be able to solve problems that involves angular momentum for particle or rotating bodies. Angular momentum of particles. So every rotational quantity that we have encountered in chapter 9 and 10 is the analog of some quantity in the translational motion of a particle. The analog of a momentum of particle is angular momentum. Angular momentum of particle is a vector quantity denoted as L. Its relationship to linear momentum P is exactly the same as the relationship of torque to force. Torque equals R cross F, so L equals R cross P. That is the same as R cross mv. The value L depends on the choice of origin, because remember this is the cross product, so it has to relate to the origin, since it involves the particle's position vector relative to O. The unit of angular momentum is kilograms times the meter per second times meters again. So that's why it's kilograms times meter per second times meter squared over second. Calculating angular momentum of a particle. So L equals R cross P equals R cross mv. Since this is a cross product, so the direction of L is perpendicular to the XY plane. So how do you define the XY plane? XY plane is defined by R and V. So the direction is determined by the right-hand rule. Basically, you point your four fingers toward L, you bend them through P, so your thumb should be pointing through L. The angular momentum of particle, L, is perpendicular. L is the angular momentum of the particle. L is perpendicular to the plane of the motion if the origin O is in that plane and has a magnitude. L equals to mv little l. What is little l? Little l is a lever arm. Remember this line, P equals mv, this is a line of action. The lever arm is a perpendicular distance from O to that line of action. So this line is the lever arm. So that's a little l. So the magnitude, you can see that can be equals to mv sine phi. mv sine phi is times r. mv sine phi is the perpendicular component of p to r. So here is p. If you can use perpendicular component, that's to r, mv sine phi times r, or you can use p times the perpendicular of r to p, the lever arm. So mv times the lever arm. So either way, you get the magnitude of L. Let's take a look at this example. A particle of mass m moves with constant speed v along the dashed line y equals to a. When the x-coordinate of the particle is x naught, what is the magnitude of the angular momentum of the particle with respect to the origin of the system? So here is mv. This is the line of action. The lever arm is from origin O to this. So we know mv, we know the lever arm. So the angular momentum equals mv times lever arm equals mv times a. The rate of change of angular momentum of a particle equals to the torque of the net force acting on it. So when the net force acting on a particle, its velocity and momentum changes. dp over dt equals f net. That's what we learned in chapter 8. Similarly, when the torque of net force acting on a particle is angular velocity and angular momentum change, we can derive it dl over dt, since L equals R cross mv. So you do the rules, you do the derivative first part times mv plus derivative plus the first part cross of derivative of second part. The first part, v cross mv equals 0, because sine, the angle between v and v is 0, sine 0 equals 0. Now the second part, r cross ma, is the same as r cross f. R cross f equals to torque. So the net torque produced the change in angular momentum. Now let's take a look at angular momentum of rigid body. Let's just talk about, think about the whole object is rotating through this axis Z that's perpendicular to this slice. Let's slice the big object into the thin layers that's rotating perpendicular to Z. So each particle in the rigid body moves in a circle centered at origin. And each instant, its velocity v is perpendicular to the position Ri. Hence, phi is 90 degrees because it's always rotating. V is tangent to the circle. So the phi equals to 90. And a particle with mass mi at a distance Ri from O has a speed vi equals Ri times omega. The magnitude of angular momentum is just mvi Ri, and vi equals Ri times omega. So this is the angular momentum of each particle equals mi Ri squared times omega. Mi Ri squared is the moment of inertia of that particle. So we add all the particles in this slice together, we get L equals to I times omega. This is kind of like a disk rotating through the axis that's perpendicular to the disk. So Li is angular momentum of the ith particle of rigid body. Li is perpendicular to the plane of the motion if origin O is in that plane and has a magnitude of mi Ri squared times omega. So for all the bodies, for all the particles on this body, that equals to I of the body times omega. Now for a body, we can add all the L's for all the slices together, and what we get is the L for the whole body equals I times omega. This is kind of similar to P equals to mv. P and V are in the same direction. In this case, L and omega are also in the same direction. So to determine the direction of L, we use right-hand rule. You curl your fingers for the, this is for the body rotating around axis. You curl your fingers in the direction of rotation. Your thumb points to the L. So we know that net torque produces changing angular momentum. That's for a particle. This is also true for a rigid body rotating around an axis. So net torque equals to dl over dt. This is similar to F equals to dp over dt. Net external force equals change in translational momentum. Net external torque equals change in the angular momentum. So if you give it apply a force that's produce a torque, angular momentum will change. That means omega can either increase or decrease, so is L can increase or decrease. Let's take a look at this example. A turbine fan in a jet engine has a moment of inertia of 2.5 kilograms times meter squared about its axis of rotation. As the turbine is starting up, its angular velocity as a function of time, omega z equals to 40 t squared. Find the fan's angular momentum as a function of time and find its value at t equals to 3 seconds. Angular momentum, L equals I times omega. Simply plug it in, 2.5 times 40 t squared, so you get 100 kilograms times meter squared over second cubed times t squared. At t equals to 3, simply plug t equals to 3, you get 900 kilograms times meter squared over second. The net torque equals dl over dt. So the first is constant, t squared. The derivative of t squared is 2t, so that gives you 200 times t. And torque at t equals to 3 seconds, substitute t equals to 3, you get 600 Newton times meter. Test your understanding. So a ball is attached to one end of a piece of string, and you hold the other end of the string and whirl the ball in a circle around your hand. If the ball moves with constant speed, is its linear momentum p constant? Why and why not? Think about linear momentum or translational momentum equals to m times v. Well, if it's moved in a circle around your hand, that v constantly changes because v is tangent to the circle. So the linear momentum has to change because its direction change. Now, how about its angular momentum, L? Since it's moving a circle at a constant speed, so omega has to be constant, and the direction of omega is also constant. Therefore, both magnitude and direction of L is constant. So the answer is yes. That's it for today. Thanks for watching. See you next time.